Mm-hmm.
So I finished my assignment, but if I haven't
Quickly email it to Sumit, KR Sumit, and write down his name. What's your name? Chinmay. Right. Write down Chinmay and those three names, and for them you take printout in the lab and give it to me.
Thank you.
Okay. Okay, so we are going to discuss today about last time we were discussing machine learning basics, and we had discussed about neural networks. No, we had discussed about optimization, gradient descent only. Right? So let's start today with neural networks. Okay, so just a quick recap what we have discussed. We saw that we have a model let's say f. It has some input x, it is a vector or a matrix, output is y, it's another matrix, and I can write y is equal to f of x. But then this f is a parametric model. What is the meaning of parametric? It means it has got parameters which can be adjusted. Right? For example, you saw a linear classifier. What were the parameters there? The slope of the line and the bias or the intercept on the y-axis. Those were the parameters of your line of that kind of separator model or classifier model. So likewise, for every parametric model, I can have parameters, and I can specify them in this way. That W is the vector of all the parameters or matrix of all the parameters, and to train the model, I have to find a loss function. Let's call it as L. This loss function, it could be, let's say, y. Let's call this y hat. Y hat is the estimated value, the model output. Y minus y hat, norm square. For example, this could be one loss function, right? And we have discussed some loss functions. We'll discuss more today. So the loss function is minimized with respect to W. So I want to find that W which minimizes the loss function, right? I want to find that W which minimizes my loss function. And the loss function is basically a function of W. Other things are almost constant, like y hat, x, y, they are constant. Y hat is a function of W, but y is constant. For a given x, you know the y. Yeah, and then to achieve it, we can either take derivative of L, minimize it by that, or if L has a very complicated form, it is not possible analytically to find the minimum. Then what do? Iterative methods. Iterative methods such as gradient descent algorithm, which means I will update my W that I move in that direction where L decreases. Right? Let's say this is my L as a function of W. W is a scalar, let's say. So let's say if I first of all I randomly choose some L, let's say some W. Let's say I chose this W randomly. For here, the value of L is this much. I find the slope, which means dou L upon dou W. Slope is like this. The slope is negative. Positive. The slope is positive. So what should W, where should W change? Decrease or increase? Decrease, so that it can go to the valley. So I will decrease my W. And if my W happen to be here, then I would like to, here the slope is negative, I would like to increase my W. So you see this formula, if slope is negative, W increases. If slope is positive, W decreases. Now what about eta? Eta is a kind of step size. How much it should increase or decrease. For example, you see here, slope is so large, so my W may go out of this screen. It may become negative, right? But I want to keep it in this small area only. So I can use some factor eta to control my jump size or step size, right? If eta is 1, then it can, if my slope is large, W will just go out of screen. But if my eta is very small, let's say 0.001 or 0.01, then W will just move little bit. Right? So eta controls the step size. So it's called the step size basically, or the learning rate. Okay, this was the basic theory of machine learning. Now, neural networks are a class of parametric models, right? Just like we saw here, F is a parametric model. Neural network is just one form of F. What is this form? It's like this. You have, let's say this is my X vector. I can also call it xi xi, and then I define one layer. Here I have my h vector, it is equal to w times x. It's a linear multiplication, just a linear matrix. W is a matrix. So what is the size of my x? Let's say my size of my x is n0, like it is n0 cross 1. What will be the size of h? Let's say it is n1 cross 1. N1 cross 1. It's a vector of length n1. Then what is the size of my w? n1 cross n0. So my w will be n1 cross n0. And this means these many learnable parameters are there. n1 into n0 times, n1 times n0, that is the number of learnable parameters in my model, right? But this is a linear model. How do I make it nonlinear? Just apply some nonlinearity on top of it. So let me call it as v. My v is equal to some nonlinear function. Tell me any nonlinear function you know. Square. Squaring is an option. Tan theta. Exponential, etc., etc. Yes, we can use any of these nonlinearities, but in practice, we want to keep our nonlinearity monotonic. So x square, is this a monotonic function of x? No. That's why people generally don't use x square as a nonlinearity. What else you said? Tan theta. Tan x, is tan x a monotonic function of x? Okay, if I confine my x to minus pi by 2 to plus pi by 2. Yes, then in the principal argument, or minus pi by 2 to plus pi by 2, it will be a monotonic function. Yeah, so you may use tan theta. But then the problem with tan theta is that its output, what is the output range or the minus infinity to plus infinity. So my output may become unstable. It may go to very large values or very small values, or magnitude may go to very large values, and that can be problematic, right? That's why we don't use tan h. We don't use tan also. What else can we use? Sigmoid function. I think we discussed in the previous classes about sigmoid function. No? We have not discussed sigmoid function. Okay, what is sigmoid function? So sigmoid of x is equal to 1 upon 1 plus e to the power minus x. If you plot it, it will be something like, okay, at 0, what is the value of x equal to 0? Half. At x equal to plus infinity, like very large, it is 1. At x equal to minus infinity, it is close to 0. So it looks like this. That's how the sigmoid function looks like. This is x. So it is monotonic. It is confined in the range 0 to 1. So people use it. It's a useful function. Right. So let's say V is sigmoid of H. There could be other nonlinearities also, but let's go with this one first. Now the output V is a nonlinear function of W, right? It is nonlinear in W. It is also nonlinear in X, right? Okay. But who is asking us to stop here? We can go further. I can define another layer. Here again I have some H dash, let's say. This is some W dash times V, and again some V dash, which is some other nonlinearity times H dash, right? So I multiplied this output with another matrix, and then again took some nonlinearity, applied some nonlinearity on the output, right? So it became even more nonlinear function. Right. Earlier it had some modeling power. Now the modeling power has increased, right? Like line has some modeling power. It can only find linear boundaries. But the moment you add some sigmoid and something, then it will become a little bit more powerful. But if you add a little bit more nonlinearity, it becomes even more powerful. In this way, you can increase the expressive power of the model. Now, you have to stop somewhere. So let's say after multiple layers, let's say, then you stop. You call this is my output y. Let's call this as h double dash first. Some w double dash times v dash. Then my y final output is some nonlinearity times h, or h double dash, sorry. Could be sigmoid, could be anything, could be any nonlinearity, or could be even linear activation. Could be a linear function of h also, like just simply h. My y is simply h. That's also fine. Or h double dash. Anything is fine. Depending on what is the range you want. You want a range of, means your y should be in the range minus infinity to plus infinity, or in the range 0 to 1, or in the range something else. Or sometimes you may want it to be a PDF or a PMF. PMF means probability mass function, right? So then you impose some nonlinearity which will also satisfy those constraints. Okay. So this is what is a neural network. Neural network is a nonlinear function of weights, is a nonlinear function of input x. To train the neural network, you simply define a loss function, then use gradient descent kind of algorithms to optimize the W. That is it. That's all about deep learning. Why is it called deep? Because when you have multiple layers, the network becomes deeper and deeper and deeper. And then that's what is called as a deep neural network. All right? Any questions? Okay, it becomes more expressive means it can model even more complicated boundaries. If I give you a line, okay, this is one simple experiment which I'm sure you have heard of. I give you a line. These are my red roses, or let's say class 1, and this is my class 2. How many lines do you need to separate these classes? Yeah. So, but if I give you only one line, you may do a very bad job. You may say, okay, one line, okay. What else can you do? If I give you, okay, take 2 lines, and I give you a nonlinear function which has like capacity like 2 lines, then you can say, okay, if I give you more nonlinearity, you will say, okay, this much, and this much, and this much. In this way, you can make a better and better approximation to the actual boundary. So in this, similarly, when you keep increasing the nonlinearity of your function, it tends to become more expressive.
Why do we require any monotonic functions?
Good point. How do you train your model? By using gradient descent algorithm. So gradients flow in certain direction, right? And that's why a W changes. No, let's say, look at this graph. Now, if I have a nonlinearity which is not monotonic, let's say it's a nonlinearity of some other shape, then it becomes difficult to get the gradients properly. Means the gradients will flow in one direction and then they will flow in another direction, not because of the actual error profile, but because of this nonlinearity. The gradients will be disturbed. Right. So, but if you have a monotonic function, then at least the nonlinearities are not introducing any change in directions. So that's one reasoning. But there are non-monotonic activations also in use. But that's very recently I saw one paper in which they used some non-monotonic nonlinearity. But otherwise, I have never seen. Generally, it is monotonic, just to avoid those complications.
So in case of the non-monotonic function, we'll reach to the local minima.
Yeah.
Not able to reach the global. Like we can't specify whether it's a local minima or global minima.
Yes.
In case if it is a non-monotonic one.
Yeah. Yeah. Yes. Anybody else?
Sir, but we define local minima or global minima using the curve of the loss function. Not of the
Yes.
Activation function.
Yeah. Yes.
So I don't think we can prove it that because of it is happening.
Yeah. Just that the non-monotonic W will introduce some local minima of its own. I think that's what he means by that, right? It will introduce some some local minima of its own into the main profile of the loss function.
Mostly because it's because of optimization purposes. It's easier to calculate than computation.
Yeah, gradients can flow in some direction. Yes. Okay. Okay, that's it. I have given a very overview kind of picture, but I would recommend that you go and watch the lectures. I will share with you the lecture videos, which will contain some more mathematical details. I won't be going into them right now. It will just take some time, so let's skip that. But I would strongly recommend that you watch those lectures. I will share them with you. Now, what are the different kind of activation functions which are used? One is the sigmoid function, which we just now discussed. Other activation functions are tan hyperbolic. Sorry. tan h of x is and if you plot it, let's say this is x, 2x. If x is 0, what's the value? 0 only. If x is tending to plus infinity, what is the value? E to the power 2x upon e to the power 2x, so it is 1. So if x tends to minus infinity, what is the value? Minus 1, because e to the power 2x becomes 0, so minus 1 upon plus 1, so it is minus 1. So the function looks something like this, tan h of x. Another function which is used is rectified linear unit. What is this? This is simply max of 0 comma x. Can you plot it quickly? Plot done? Okay. It's basically when x is less than 0, it is equal to 0. When x is greater than 0, it is equal to x. And at 0, it is 0. That is ReLU of x, rectified linear unit. You have read rectification in your ESC 201, right? Rectification. Right? You had your sinusoidals and rectified wave. What is it called? Half wave rectifier and full wave rectifier. Yes. So rectification means clipping. So this is some kind of clipping happening. And if generally we can, all these functions are already implemented in standard neural network libraries like TensorFlow, Keras, PyTorch, etc. They have also documentation of different activations which are available. So you can even go through those documentations to see other activation functions. Okay, now let's come to some next stuff. So we can use these functions for regression, and we can also use them for classification. So what is classification? Let's discuss first multi-class classification. So multi-class classification means we have got multiple classes and the data can belong to one of those classes. Let's say, give me examples of multi-class classification. Animal classification, whether it's a dog or a cat or a zebra or a lion. Okay. Digit classification, if I write something, whether this is 1 or 2 or 3 or 4. Right. Vehicle classification, whether this is a car or a cycle or a scooter. Fruits, fruit classification. Roses, lotus, jasmine, they are called multi-class classification. This is opposed to multi-label classification, where one thing can have multiple labels. For example, if I ask you, okay, rose is there. If I ask you, does it have a red color? Yes or no? Or does it have leaves or not? Yes or no? Does it have, what else can it have? Is it an English rose or Indian rose? Right, again, 2 options are there. Like that, it can have multiple labels. Similarly, for a person, we can ask, is it a male or a female? Then, is this person wearing spectacles or not? Is this person having beard or not? Is this person having long hair or not? So, etc. It's like we can make, so for every question, there could be yes, no answer. right? Let's first discuss multi-class classification. How do we model it? We generally model it using a PMF, probability mass function. That what is the probability of a class C given X? Let's say X is the input image and C is the category, whether it's a rose or a lotus or a jasmine, right? P of C given X, and what are the constraints? It should be less than 1, very good. Because it's a PMF, it should always lie between 0 and 1. What else? Sum over all classes should be equal to 1. What else? Anything else? No. Okay. Now if I give you a neural network, it has some input X, some output Y hat. How will you model P C given X using F, using Y hat, or using F? How will you model, try to get the information of P C given X from Y hat? If we can constrain our Y hat to follow these constraints, basically the sum of all these, so Y hat is a vector, right? If we assume that every index or every entry of this vector corresponds to one class, right? Let's say Y hat has a vector of length 3, let's say. Then I say this is a rose, this entry corresponds to rose, this corresponds to lotus, this corresponds to jasmine, right? And then I put a constraint that all these entries should be greater than or equal to 0 and less than equal to 1, and all these entries should sum to 1. Then I am able to express my Y hat as PC given X. Clear? Clear? My Y hat is equal to, basically Y hat, the Cth if I am able to constrain it in this way. How can I put that constraint? Because my H means, you know that Y hat is some nonlinear function of H, right? We have seen here, right? H, what is H? This is H double dash, right? And Y hat is some nonlinear function of H. So what nonlinearity should I choose so that even if H has a range -infinity to +infinity, my Y should follow that range between 0 and 1 and sums to 1. Yeah, so if you know the answer, then you know it. But if you don't know, then you can design it. These are some examples for your practice. When you work in real world problems, you may not know what to use and you have to design something on your own. So what we use is, so we use this e to the power, so yc is equal to e to the power hc divided by say d something. This is called a, so now look at the properties of this function. Is it between 0 and 1? Can we say every yc is between 0 and 1? Yes. Can we say all the yc's sum up to 1? Yes. So this function satisfies those constraints. That's why we use it for multi-class classification. And this nonlinearity is known as softmax nonlinearity. because it satisfies the constraints of probability mass function, softmax. All right. And you can see the output y c depends on h of c, but it also depends on other h of other d's basically. It also depends on others. So there is a dependence between classes. The output depends on all the, or every y index depends on all the h values, not just single h value. Okay. Now, let's say I want to design a loss function for this problem, classification problem. How will I do that? For training my neural network, I need to design some objective function or loss function which I want to optimize, so that if that is satisfied, I will say I am happy now, my model has been trained. So essentially you are here trying to compare two PDFs. You have some target PDF. What is the target PDF? Let's say you know it's a rose. What is the PDF? 100, right? 1 for the rose, 0 for lotus, 0 for jasmine. Means the probability. Probability of rose is 1, probability of lotus is 0, probability of jasmine is 0. So this is the target PDF. And what is the output PDF? This y. Now how will you design a loss function which measures the distance between two PDFs? If it were two numbers, just two real numbers, how do you measure their distance? Euclidean distance or absolute distance. But let's say you have two PDFs, how do you measure their distance? Likelihood. You have two PDFs, let's say P of x and Q of x. What is maximum likelihood here?
You can say that we can maximize the probability that we are predicting class C given no class C, something like that.
Yeah. You are close to answer, but not really. Maximum likelihood is useful when you have samples from one PDF and the parametric form of the other PDF. Then you can use these samples to maximize the likelihood, right? But in this case, we have two PDFs. Let's say two parametric forms of both the PDFs. So how do you measure their distance? How do you measure how similar or dissimilar are two PDFs? You have read it in your courses. Divergence measures, no? Kullback-Leibler divergence. Even cross entropy, somebody could have said. Cross entropy or Kullback-Leibler divergence. Have you read KL divergence? Raise your hand if yes. Don't raise if no. Only 2 people have, 3 people. Oh, okay, strange. Okay, so what is the KL divergence between two distributions P and Q? This is equal to P of x log this is the KL divergence between P and Q if the random variable x is a continuous random variable. But if it is a discrete random variable, it becomes a summation instead of an integration. That is the KL divergence between two distributions P and Q. What are the properties of KL divergence? non-negative. It is always greater than or equal to 0. It is never less than 0. All of you know that? Can you prove it? Can you prove that this is always greater than 0? How will you prove? You can use Jensen's inequality. Have you read Jensen's inequality? In which course? PropStats course, right? What is it called? MSO 201. Huh? MTH 101. They teach Jensen's inequality. I don't remember. Okay. Maybe 15, 18 years now. Yeah, but at least I remember they teach in MSO 210. 210 or 201? Huh? 201. A PropStats course. Yeah, in that course they definitely I was tutor for that course 2 years ago. So I remember it was there. Jensen's inequality. Jensen's inequality basically says if you have a whatever it's called, convex or concave? Convex. Then you take these 2 points. If you take average of these 2 points, let's say this is f of x, this is x. So let's say I have x1 and x2. That f of x1 plus f of x2 by 2, which means this value is always less than or equal to f of x1 plus x2 by 2, which means this value. So this is this value and this is this value. That's the Jensen's inequality. And using this you can prove that KL divergence is always greater than or equal to 0. Should I do it, or I thought this is already known to you. This is a known result. Is it fine if I skip it? Okay. Yeah, so using Jensen's inequality you can say that KL divergence is always greater than or equal to 0, and it is equal to 0 when Px and Qx are exactly same. So this KL divergence is like a distance metric between PDFs, probability distribution functions or probability mass functions. When they are exactly same, then KL divergence is 0, and when they are different, KL divergence is greater than 0. And as they become more and more different, KL divergence keeps increasing. Okay, I will not go further into details, otherwise it will be a class on KL divergence.
KL divergence, what PDF I is going to do?
Could be anything, either P or Q. Actually, KL divergence is non-symmetric. Means KL divergence of PQ is not the same as KL divergence of QP. So whatever way you take, it's a different expression.
Depend on what is known and what is
Yeah. Yes. And you can manipulate that. You can construct new things out of it. Yes. Okay. Now that's it. Okay. Now what is the loss function for our neural network? So it will be, what's the time now? 44. Okay. I want to wrap it up quickly. Okay. Loss function is KL divergence between y and y hat. Y hat is a PMF, y is also a PMF. Can I take the KL divergence between the two? Okay, what will that be? This is equal to yc log of, this log is to the base e, log to the base e, yc upon y hat c, summation over all c. This is hat here. All right. Let's simplify it. It becomes equal to summation over c yc log yc minus summation over c yc log y hat c. And you want to maximize it with respect to w. Which of these terms are a function of w here? Yc hat only. So yc, this term does not play any role in optimization. We can just drop it because it's not a function of w, so it won't play any role in the optimization. Now this thing minus yc log y hat c. This is called as the cross entropy. Right? So KL divergence is kind of a sum of self entropy and cross entropy. Self entropy of yc and the cross entropy between yc and y hat c. Just a term, it means just a name given to this term. It's called cross entropy. So my loss function is a cross entropy loss function. Okay? I'll come back to this, but first let me go to multi-label classification. So what is multi-label classification? Here every label can have a value 0 or 1. Let's say, does this person have spectacles or not? If I show you give you a picture, does it have a does this person have spectacle or not? You can say yes or no. Does it have mustache or not? Yes or no. Does the person have long hair or short hair? So basically long hair or not? Yes or no. Cap or not? Yes or no. A necklace or not? Yes or no. Earrings or not? Yes or no. Means you can have so many labels. Remember that example of Sarah Chaudhary. Is it a line drawing or a painting? Or does it have turban or not? Is it a Pran Comics or Disney character? So all those labels could be there. How do you model it with neural network? First, what are the constraints? I can say I have probability of a label given x, or probability of label equal to true. Let me define it. The Lth label, let's say my first label is mustache, second label is spectacles, third label is necklace, fourth label is lipstick, etc., etc. So all these labels, so the Lth label is true or not. That could be one PMF. So it is a kind of, it's a binary random variable. The Lth label is a binary random variable. Which means it is true or false. Either it is true or it is false. So which means how many parameters are there to define this PDF? How many parameters? Only one parameter, right? It's either the probability of false is 1 minus probability of true, right? Okay. Now I have got n number of labels. This means I will have n number of PDFs. And each PDF has a property that this is less than equal to 1, greater than equal to 0. Right? Do I have to consider the summation constraint? No, because if I know this value, other value is simply 1 minus this. So I don't care about the summation constraint. Okay. Then I have L number of labels. How do I model them with a neural network? How do I model them with a neural network?
You just choose sigma delta and multiply.
You already have done machine learning course.
But we are not putting the summation condition, so that's why.
Have you done machine learning before? Or you're telling this from your previous knowledge, or are you designing it? Both. Okay. Good. Good. Yeah. So I need my vector y. Y is a vector of length n. Let's say if there are n number of labels, then vector of length L. And each entry should follow the constraint that it should lie between 0 and 1. That's it. What is a function which lies between 0 and 1? Sigmoid. Or if you have a 10h, you can just do some manipulation and squash it to 0 and 1. How? Let's say add 1 to it and then half. That could be another way. But let's use sigmoid, it's straightforward. So my y L is simply sigmoid of h of L. That's it. Now see, my every output YL, does it depend on other entries of H other than the Lth entry? No, it's independent of other entries. It only depends on H of L. So that's an important thing to notice here. Now, what should be my loss function to train the network? What should be my loss function to train the network? Earlier I had single PDF. Now I have how many PDFs or PMFs? N number of PMFs, right? N number of PMFs. How do I? What should be my loss function now? Yeah, same. Take KL divergence over every random variable or over every PMF, and then average over all the labels. Right? So it will be average over all L, KL divergence between YL and Y hat L. Sorry, this was Y hat. Right? YL is a PMF, Y hat L is a PMF. Okay, means, yeah, Y is a scalar value, but it defines a PMF, right? Because that is the probability of being true, and probability of being false is just the other counterpart. So let's fill in the values. This is summation over L. Weighted average, yes, yeah, weighted average also.
So what the labels are they like a 0 1 vector, or are they a vector of different discoveries?
You mean Y or Y hat?
The ground.
Y is 0 1.
So then, so what if we can use instead of sigma, we can use the sigma function on h of L, divide 1 plus sigma h of L by 2, and then simply define the Euclidean distance.
If you take sine of H, SGN, sine is the SIGN sign, not the SINE, SIGN signum of H. Is it differentiable? Is it differentiable? No. And okay, it is not differentiable on 0. It is differentiable on other points. What is the gradient? Always 0. Can you use gradient descent? When the gradients are always 0, I will not know which direction should I move to. So that's why the non-differentiable functions, or such functions where the gradients are close to 0, such functions are not desirable. From that perspective, even sigmoid is not a desirable function. It has very low gradients. That's why people use ReLU. ReLU is max of 0, x. So the gradient is always 1 on one side. On one side it is 0, but on one side it is always 1. So that's why people prefer using ReLU instead of sigmoid in the layers. Okay, now let's come back to this. This is y log y plus or minus y log y hat. And this term is not playing any role, so this is simply minus summation over L. Now, when I say y, it is two things. Actually, this was py, it is not y, actually, it is py. So, which means probability that my label is 1. What is that probability? Probability that label is 1. That is y. And what is probability that it is equal to 0? 1 minus y. So that is the loss function. Oh, L. I'm writing L in the subscript. You can write it in the brackets or subscript also. Both are fine. Huh? Summation over?
Because K is also a summation, right? So summation, another summation outside.
That summation is opened here. Okay, that means you mean to say here, right? Label or Lth label L is equal to true or false, huh? Yes, thank you. So here there is a summation, label L is true or false. And then I opened it up, either true or false. That's it. What is this loss function? What can we call it? Cross entropy only, or average cross entropy, but it's cross entropy. But then these two loss functions are very commonly used in classification problems, as you have noticed, as it is obviously known. Now we have to somehow distinguish between the two. So we have to give some label so that people don't get confused whether I'm referring to this problem or that problem. So what is the label we give generally? This we call as binary cross entropy, because you have binary random variables and then you average over all the cross entropies or over all the labels, right? And this cross entropy is called the categorical cross entropy, because this is a categorical random variable. It follows categorical distribution, or basically categorical distribution is a distribution where a random variable can take one of the n values, but only one of them, not simultaneously multiple values, but only one of them. That's the categorical random variable. And this is a binary random variable. So we use this to name the cross entropy also, just to avoid confusion. Okay, so now we are ready for our practical exercises. Is that done? Anybody has any questions up until here? No? Now, we will have some lesson on beat estimation. How do I tell you? Okay, let me first continue with this. Let's talk about beats. So what are beats? You can have let's say a person is playing beats. It could be, I'll give an example, Dha Din Dhinna, right? Dha Din Dhinna. Oh, Dha Din Dhinna. How many beats are there? 4 beats. So I have a timeline. This is like time. I divide my time into 4 units of equal lengths. Let's say this is 0. And then again 0 starts. Right? So I call it as let's say here I play dha, here I play dhin, here I play dhin, here I play na. And again on 0 I will again play dha, dhin, dhin, na. So dha, dhin, dhin, na, dha, dhin, dhin, na, dha, dhin, dhin, na. How do you expect your waveform to look like, the audio waveform? It will be something like this. You have waveform like silence. Suddenly you have dha, then dhin, then dhin, then na, then again dha, like that, right? There will be sudden bursts of energy. Silence, but then suddenly dha, like it's a sudden burst of energy. Then again dhin, burst of energy. Then dhin, then na, sudden bursts of energy, right? Using which you can detect these strokes. Okay, so now I will define some concepts. I'll give one more example here. Ghe ghe titta. These are two different things. Ghe. Parampreet can come here. He's an expert in tabla. I'm not. I just learnt it from him today morning. And Rahul is not here. But okay. Sahi hai na? Okay. Can you pronounce this? How do you say?
So it is ge tit.
No, do it properly. It's in rhythm.
Ge tit ge na na. Ge tit ge na na.
Yeah.
It's basically 2 strokes in 1 beat.
So this is 1 beat, 1 beat, 1 beat, 1 beat, 1 beat, 1 beat. How many beats are there? How many beats? So there are 8 beats. How many strokes? 16 strokes total. So what is stroke? This alphabet, every symbol is 1 stroke. Ghe is 1 stroke, ti is 1 stroke, ta is 1 stroke. Total 16 strokes. And so you see in this, there is something 0, and then this 0 repeats. Means there is some starting point which is used to hold music, like to synchronize everything together. Singer is singing, tabla player is playing tabla, or drumist is playing drums. So this is called downbeat or sum. This is called the sum. So this one is called sum. Sum means the starting beat or the most significant beat, you can say. So it is said that other beats may go slightly here and there, but some should not go wrong, right? It means the timing of some should be exactly at the right place. Other beats may be slightly off, but this one has to be right on spot. So this is the sum here. So in English, you have terms. Look, these concepts are exactly same in English music also, in Western music also. This beats are called beats only, but another technical term uses tactus. And strokes are also called strokes, but they are also called tatum. And this sum is also called downbeat. Right? Now, interesting problems in music are, what are the problems possible? If I am playing some music, it has a pace. I can say, what was the earlier example? Dha, dhin, dhin, da. Dha, dhin, dhin, na. Dha, dhin, dhin, na. Or I can say it very slowly. Dha, dhin, dhin, na. Okay. Dha, dhin, dhin, na. Like very fast, very slow, intermediate. So many speeds are possible. And these speeds are measured in the units of beats per minute. How many beats we have per minute? Number of strokes can vary. I can say dha, dhin, dhin, na, dha, dha, dhin, 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 na. number of strokes can vary, but the number of beats remains similar, it's a constant. So estimate the BPM or beats per minute. Detect strokes or detect downbeat. I want to synchronize everything, so detect the downbeat. Where is the downbeat happening? All these problems are problems of interest. Now we will do some exercise. What was that example you gave? Dha? Oh, no, this one. Dha, dhin, dhin. No, what was that? Dha.
So it was dha, din, dha. This is the
Normal one.
Normal beat. So now we'll just
Change the timings.
same strokes. We'll just change the timings. Dha, din, dha, dha, din, dha. I'm playing with the delay, nothing else.
Yeah.
The strokes are same. Strokes were dha, din, dha. This BPM is same. I'm not changing it. I'm not changing the beats, but I'm changing the strokes, the position of strokes. So it's like dha, din, dha, dha, din, dha. Again, the number of beats is same, but the
Yeah.
placement you can see.
Yeah. Can you first of all, can you identify the difference between the two? Dha, dhin, dhin, na. Dha, dhin, dhin, da. These are two different, right? Two different patterns.
The difference between two strokes is not very.
Is timing.
Basically, yeah, the sum will be same. That won't change. The BPM will be same, but the strokes they are being played at, you can say different delays. Yeah.
So I will just plot this thing now. I think that will be helpful. This is the time axis, 0, 1, 2, 3. Again 0. So here I am playing dha, dhin, dha, dhin, na, right? Everything is exactly at the right timing. But in the other one, we are playing dha, then a gap, then dhin is somewhere here. Right? Dha, dhin, dha, dha, dhin, na. Right? Dha, dhin, na. Right? So how do we write the notation? This is simply dha, dhin, okay, dha, dhin, na, right? And this one will be dha, and there is a blank comma dhin, which means we have divided this beat into two parts. This beat divided into two parts, this two halves, and the first half is empty, second half dhin. Do you understand it? Dha, then empty, then in the second half we have dhin. Then again here empty, then second half dhin. Then here na. Dha, dhin, na. Right? Now, exercise for you. Open Praat, record your audio, means when you are pronouncing this pattern, and then try to generate this notation from the audio. Can you give some exercise? Dha, din, na, dha, din, na.
Another tal we can do.
Means just keep it 4 beats for simplicity.
Okay.
Later we can make it more complicated. Dha, din, na, dha, din, na. Right? How do you write it in this notation? If you do it just by hearing, it may be a little difficult, but if you do it with the help of tools, it will be easier. So, given any, I'm not saying use machine learning or use signal processing to do it, just do it yourself. Means you can use Praat or something to record the audio and to visualize the audio, and then you generate these notations. So Parampreet will send you some audios. Not notation. They will send you the notation. So you send them audio, and they have to send the notation. All right? That will be an exercise for you. Okay? Now the next. Okay. Is that problem clear? Okay. Now we are going to start. What are the signal processing based methods to do these tasks, which we just now defined? How do we estimate the BPM from the audio using signal processing methods? How do we estimate the strokes in the audio using signal processing methods? How do we detect the downbeat, etc., etc.? Right? So if you remember, we discussed here that your audio is mostly silent, and suddenly then there are bursts of energy, right? You want to define some measure of these bursts. You want to derive some measures from the audio directly, which you can use to, let's say, detect the strokes. What would you use intuitively? Huh?
Can we measure the energy?
Energy, yeah, energy. Suddenly there will be energy is very small, suddenly large energy against small, large energy against small, large energy. So energy is a good measure. Let's start from there. How do we define energy? Energy is defined as that. So first of all, let's say you have something like this. First of all, you have to take a small window, very small window, right? Around the around every time. Let's say small window here, small window here, small window here, like you do it in STFT, right? So what is the mathematical notation for that? My signal is x of n. What is the expression for this small filtered signal? Huh? Yeah. So it's x of n plus m, because I will also shift it a little bit, and then w of n. And then you square it, sum over all n. Right? But because your w is finite, you can take a finite sum also. Let's say the w is a window from minus n to plus n. Then just take a small window between minus n to plus n. The other things are anyway 0. No need to waste your computer resources. Or let's say minus n to plus n. Right? Okay, I will not write this because that's obvious. Because you are using w. W is a finite window. That is the expression for w. Right? Can you appreciate this? That as my m is increasing, I'm going forward in, my window is moving forward, right? Why? Because my signal is moving backward. So my window is moving forward relatively. Okay, this is the energy measure. If you draw the energy measure, it will look something like burst, and then again a burst, then again a burst, right? But still, it can have some spurious levels also. So to clean it or to make it sharper, we use the derivative. Let's say I am singing, so already energy is high, and then suddenly there is a tabla stroke, dhum. Then again I am singing, energy is high already, suddenly drum stroke. Then again the energy boosts up. So instead of measuring the absolute value of energy, we measure the gradient of energy. That helps us to do a robust detection even when there are other sounds present. Right. So therefore we use delta E. It's called the time up. Delta EM is equal to E of m plus 1 minus E of m. But generally, we are only interested in onsets, which means energy suddenly increases. I'm not interested in the decay because I am interested to detect my onsets, not the decay part. So for onset, which is very sharp, my derivative will be positive. So I'm interested only in positive derivatives. So I take a, what does this mean? Only if it is greater than 0, then consider it. If it is less than 0, or then just make it 0, ignore it. Only interested in energy rises, not energy falls. So this delta EM can be used to find onset times of strokes, right? What is this function called? Let's give it a name. It's called the energy-based novelty function. So energy-based novelty function means suddenly some burst has happened and something new has happened. Means it's just basically it detects the bursts, the new bursts which come. Yeah. So the exercise will be sent by Parampreet very soon. Okay. And you have to submit it. I'll give you some time, don't worry. Maybe I'll convey that by email. Okay, next announcement is that coming Thursday there won't be a physical class. I will share some lecture videos with you. You can watch them instead of coming here. Because I am traveling, I will not be here. But I'll share the videos, and on the next Monday I will quickly go over those content of the videos, and then, but I will not discuss the details, so you must watch the videos, and then we will meet on next Monday. And we will have a quiz on following Thursday. Okay? There will be a quiz on the following Thursday. Come prepared. And the topic of quiz will be everything done this week. Means including the videos also. Those videos are a part of the quiz. So everything done until now, plus the videos which I'll be sharing. This is the topic content for the quiz. Okay, next Thursday. Means not this Thursday, but the following. Thank you.